Welcome to another deep dive. Today we're looking at something really fascinating in the world of large language models, LLMs, those AI systems making waves with their ability to generate text and translate languages and even write code. But as powerful as these LLMs are, there's this curious inefficiency kind of hiding within these huge models, like a curse that affects their deepest layers.
Yeah, that's right. We're pouring all these computational resources into training these LLMs, and there's more and more evidence that almost half of their layers aren't as effective as they could be. It's almost like we're building a skyscraper and just leaving a bunch of floors empty.
Okay, so this curse of depth, as they're calling it, what exactly is going on here? What's the evidence for these deeper layers not really pulling their weight?
Well, researchers have been doing these really interesting experiments that show this. One thing they found is that when you remove the early layers in an LLM, the performance really tanks, which makes sense. But here's the thing, when you remove deeper layers, it doesn't have the same effect.
So you're saying you can chop off a bunch of layers from the end of these huge models, and it doesn't really hurt their performance. That's kind of wild.
Yeah, it is. And it gets even weirder. Studies show that these deeper layers are actually really resistant to disruptions. Like if you rearrange them or even drop some completely, it's like they're not really contributing to the learning process as much as we thought.
So there's definitely something going on here. What is causing this curse of depth? Why are these deeper layers so seemingly ineffective?
So the culprit seems to be this common practice we use called pre-layer normalization or pre-LN.
Right, pre-LN, I've heard of that. Can you remind me what that is again?
Sure. So basically, pre-LN is where we normalize the input data before it goes into each layer of the model. You can think of it like prepping ingredients before cooking. You want to make sure everything's in the right format for the recipe. Pre-LN is actually great for stabilizing training, but it's got this side effect we're just starting to understand.
Okay, what's the catch with pre-LN?
As information moves through all the layers, the variance of each layer's output actually grows exponentially with depth because of the pre-LN.
Hold on, variance. Can you explain that a bit more?
Okay, imagine a group of people walking down a path. At the start, they're all walking at about the same speed, but with each step, they take the difference in their speeds grows. Some speed up, some slow down. This spread in their speeds is kind of like variance. With pre-LN, it's like with each layer the model processes, the spread in the output values increases a ton.
I see. So as we go deeper into the model, the output from each layer gets more and more unpredictable.
Exactly. And this huge increase in variance in the deeper layers leads to something strange with the derivatives of the transformer blocks. Transformer blocks are basically the building blocks of these LLMs, and their derivatives tell us how a small change to the input affects the output.
Derivatives, right? We're getting into the math a bit here.
Yeah, well, basically, because of this exploding variance, the derivatives in the deeper transformer blocks start to look a lot like an identity matrix.
An identity matrix? I'm not sure I understand.
Think of it like a do-nothing component. It takes an input and spits out the same thing. When the derivatives start looking like an identity matrix, it means those deep layers aren't really doing anything. They're not contributing to the learning, which might be why we can sometimes remove them without much impact.
So it's like those people in a group project that just coast while everyone else does all the work. We need to make these deeper layers pull their weight.
Exactly. And luckily, researchers have come up with a really clever solution. It's called LayerNorm Scaling.
Interesting. Tell me more about LayerNorm scaling. How does it solve this variance problem?
So unlike pre-LN, where you normalize the input, LayerNorm Scaling scales the output of each layer normalization by a certain factor. And this factor is basically the inverse of the square root of the layer's depth.
Okay, so the deeper the layer, the smaller the scaling factor applied to its output.
Yeah, exactly. It's like we're slowly reining in that variance explosion as we go deeper into the model.
It's like that walking path example. You're introducing stricter and stricter speed limits as people move along, making sure the differences in their walking speeds don't get too crazy.
That's a great way to think about it. By keeping the variance in check, layer norm scaling stops those deeper layers from becoming useless. It makes sure they're actually involved in the learning process.
This is really cool. It's like we're giving those lazy layers a pep talk and helping them reach their potential. So what kind of results are we seeing with this layer norm scaling?
The results are actually really promising. Researchers have tested layer norm scaling with all kinds of LLM architectures, and they're seeing improvements in both pre-training and fine-tuning.
Can you remind us what pre-training and fine-tuning are?
Sure. Pre-training is like the first stage of training where the model learns from a huge data set of text, like a giant digital library. It's like building a strong foundation of knowledge. Fine-tuning, on the other hand, is more specific training where we tailor the model for particular tasks like translating languages or answering questions.
Okay, so layer norm scaling is like a performance boost for both general and specialized learning.
Exactly. During pre-training, models that use LayerNorm scaling get lower perplexity scores, which means they're better at predicting text. And when it comes to fine-tuning, they just perform better on all sorts of tasks.
Wow, that's impressive. It sounds like LayerNorm scaling is a game changer. What else is good about it?
Well, one of the best things about LayerNorm scaling is that it's super simple to use. You don't need to mess around with complicated settings or add extra stuff during training. It's a simple tweak with a big impact.
I love how such a small change can make such a difference in AI. It's like finding that one secret ingredient that takes a dish to the next level.
It really is, and it makes you wonder if a small change like LayerNorm scaling can unlock so much potential, what other inefficiencies are hidden within these models just waiting to be found?
That's a great point. It seems like we're just scratching the surface of what these models can really do. What are your thoughts on that?
Yeah, it's a question that keeps a lot of researchers up at night, I think. We're always trying to push the limits of what AI can do, but there's still so much we don't know about how these models really work. Discoveries like LayerNorm scaling show us that even tiny changes can have huge effects. It just goes to show how important it is to keep questioning our assumptions and looking back at the core of our models.
And in this case, that means looking at how we're handling normalization in these deep neural networks.
Right. It's like we've been using this tool layer normalization for ages, and only now are we realizing there might be a better way to use it.
Okay, so LayerNorm scaling seems like a good thing. But let's step back for a second. Why should the average person even care about this? What does this discovery mean for the bigger picture?
Well, this finding has big implications for the future of LLMs and how AI is shaping our world. For one thing, it looks like we can train LLMs way more efficiently, and that means using less computing power and less energy, which is a big deal as these models get even bigger and more complex.
So we're talking about making AI more sustainable.
Exactly. The energy it takes to train these huge models is a growing problem. And layer norm scaling, by making those deep layers more effective, could really cut down on that energy use. It's about making AI not just smarter, but also greener.
That's awesome. It's not just about the environment either, right? Wouldn't more efficient training also make these models more accessible?
For sure. By lowering the computing needs, we could make LLMs available to more researchers and developers who don't have access to the huge computing power that some of these big tech companies have. This could lead to more people and organizations from all sorts of backgrounds working on AI, which would bring more diverse perspectives and maybe even speed up innovation.
So it's about breaking down those barriers and creating a more inclusive AI world. That's pretty exciting.
Definitely. And don't forget about the potential improvements in performance. By letting all layers work effectively, LayerNorm scaling might let us get better performance from smaller models. That could mean AI systems that are more efficient and responsive, opening up new doors in things like natural language processing, machine translation, and even drug discovery.
Okay, I'm getting really pumped about the possibilities here. But before we get too carried away, let's take a closer look at how LayerNorm scaling actually works. You said we scale the output of each layer normalization by a factor. But how do we figure out that factor? What's the magic formula?
The formula is actually pretty simple. Remember, the main problem with pre-LN is that the output variance grows exponentially with depth. Layer norm scaling takes care of this by scaling the output of each layer normalization by a factor that's the inverse of the square root of the layer's depth.
So the deeper the layer, the smaller the scaling factor.
Yep, exactly. It's like we're gently putting the brakes on that variance explosion as we move deeper into the model.
It's like that walking path analogy again. You're putting in tougher speed limits as people move along so the differences in their walking speeds don't get out of control.
Perfect analogy. By managing the variance like this, layer norm scaling keeps those deeper layers from becoming useless. It makes sure they're part of the learning